Welcome to section 4, From Factorization to Independence, I-map. In the previous section, we ended up at this data set if it's given, and also if we know all the conditional independencies, how can we choose the correct factorization that will reduce the number of parameters for the joint probability distribution? Okay, so given a factorization, how can we obtain the conditional independencies? So for example, assume that we know that the joint probability distribution of x1 to x4 is written in this form. Well, one thing that I can do is just to compare the factorization to the original chain rule factorization. If you recall, p of x1 to x4 can be written in this form. x4 condition on the remaining, x3 on x2, x1, and so on. Now, by comparing these two, I realized that what is changed here is this last term, or the first term from left, x4, and here these two variables, x1 and x2, are taken out. So I can conclude that only x3 is the parent of x4 here, right? And x4 should be independent of x1 and x2. So I can write down this conditional independence, and I can say that it belongs to IP, the independencies of the distribution P that should be factorized in this way. Now, we need to be careful. This is sufficient for P. The argument we provided here shows that it is sufficient for a distribution P to factorize according to star, which is this form. Meaning that if we know that this holds, if we know that such a conditional independence holds, then by using the chain rule, applying it here, we ended up here. Okay? But is it also necessary? So meaning that if the following factorization is given, can we conclude that this conditional independence also holds? Okay? Now for that, we need to prove it, and here's the proof. We start from the probability of x4 condition on x3, x2, and x1, and we want to end up at p of x4 given x3. So namely, we want to show that x1 and x2, they can be taken out, and therefore they're independent. Okay? How can we do that? So we just use the definition of conditional probability. So it's all of the variables divided by the 3 here, and we use then the equation star, so we can write this down as, we can factorize it in this form. Now, as the denominator, just note that we know that it's marginalized over x4 actually, so we sum it over x4. But doesn't matter, we put it there, and then we can still factorize it in this way. Now, all these 3 terms are independent of x4, and they're the same in the numerator and denominator. We cancel them out, and we end up here. Now, x4 condition on whatever summed over x4, this is just 1. So what remains is the denominator, and it is x4 condition on x3. So that's how we show that x2 and x1 can be taken out here. And the key is the factorization that we use in the star. So indeed, it is both necessary and sufficient. If we know star, we can conclude that this independence should hold. And if we know that this independence should hold for P, we know that it can be factorized. Now, can I use the same procedure to find the conditional independencies of any arbitrary factorization? Well, it's not that straightforward. For example, in this case, we don't have the CPD starting from x1, it's from x3, and it may not be clear what the right ordering of these are. So in this particular case, the original chain rule based factorization, it doesn't start from like x4. Okay, so how can we find it? Well, there's a specific property in the chain rule factorization that we can use here. One obvious rule is that for sure each variable, like here x1, x2, all of them appears only once on the left side of this notation, on the conditional notation. But the more important one is this. Once a variable, say xn here, appears on the left of the conditioning, then it never appears on the remainder of the CPDs on its right. So for example, xn once appeared here, it doesn't appear in anywhere else on the right. x3 once appears here, it doesn't appear on any of the other ones on the right. Okay, and based on this, we can now find the correct ordering of the chain rule factorization. So for example, x3 cannot be the first one because it later on appears here. And also, for example, can x4 be the first one? No, because it appears here. And can x1 be? No, because it appears here. So the only one is x2. And you can continue with the next one. So for example, x1 again cannot be the second one because it appears here, but it can be x4 because it doesn't appear on the remaining ones, and so on. So based on this, we find the original chain rule-based factorization, which is in this way. And now by comparing the two, these gray ones become clear that they should have been the ones that should be independent from. Like here, x4 will be independent of x3 given x1, and x1 and x3 should be become independent of x2 given x4. Okay? But what did we just see? If we want to summarize, is like each variable xi, okay, conditioned on its parent in the original factorization, is independent of the remaining variables that never appeared in any of its left CPDs. Okay, so x4 becomes independent of x3 here. Well, condition on its parent becomes independent of x3. But what is x3? Well, x3 is the one that appears on its right, but it never appears on the left. Okay, in the original factorization. It is never, and here we mean on this notation, on the conditioning notation. So x3 already appeared here, but the one on the left is x2. And the same holds for in this one. Well, here it doesn't have any on the left. So x4 will be independent of x1 and x3. Okay? But you see, it's getting so like complicated and messy. What can we do it in a neater way instead of these right and lefts? And the answer is yes. Thanks to the graphical visualization that we just developed, the BNs, we can find a way that we don't need to talk so much about left and right. This is the algebraic way of solving the problem. But there's also an easier way. Now, let's see it in practice. What is the equivalent graphical condition? So we have this factorization. The equivalent graph for this, the Bayesian network, will be here, this graph. So if you recall, we put x3, the first one here. The next one will be x1, x4, x2. And how do we link them? We just link from the parent to the variable of to each variable. So here x1 is the variable, and then the parent is x3. x4 is the variable, the parent is x1, and so on. And we also put the CPDs next to each of them. Okay. Now, from here, we can make a conclusion. Originally, if this was the chain rule, then here for x4, I should have had a link from x3 as well, right? And for x2, I should have had a link from x1 and x3 as well. Now, the fact that the two, neither of these are appearing here, it means that x2 is independent of them, given its parent. So, for example, x4 conditioned on its parent x1, which is this one, look at the CPD, it's independent of x3. This link is not there. And x2, in the, again, chain rule, it was supposed to be having a link from x1 and x3, but neither of them are showing up here. So I can just say that I can take them out. So the links that we originally expected from the chain rule, they're no longer there. Now you may say, but still, I don't know what is the original chain rule here. In this case, at least it was clear. Well, we can try to generalize this a little bit. I'm just trying to provide the intuition here. Okay, we'll later see how rigorously to write all this. These x1 and x3 in this case, and x3 in this case, what are they? You know, they're really what we can define here as the non-descendants. So let's start with this one, for example. X4, X1 is clear. For X4, X1 is just the parent. Okay, so I can write down X4 condition on its parent. But what about this one? So X4, X1, and what is the role of X3? Well, it's the non-descendant, and of course excluding the parent. So the descendant of X4, or the child in this case, is X2, and the non-descendants will be this part. Okay, now X1 is already appearing on the right side, so X3 will be the non-descendant. So X4 is becoming independent of the non-descendants given the parents. If you think about it, this node, in order to know what's going on about this node, only the parents are enough. It becomes independent of the remaining nodes. It doesn't matter who, any other node, whether it is linked to the other parts of the graph or not. Of course, excluding the descendants. X4, a node is always depending on its descendants. There is some relationship between them, so they cannot be independent. But if we know the parents, if you recall that brother or sister, if we know the parents, then it doesn't matter anymore if I provide any extra information like what is the color of another human, or even if it's indirectly related, like the grandfather or the aunt or a friend, it doesn't matter anymore. So that's intuitively the idea here. Now let's check it on this other one. X2 becomes condition on its parent X4 becomes independent of its non-descendants. Here I don't have any non-descendant. Okay, all the other ones will be these. Again, X4 is already appearing here, so these are the non-descendants, but since X4 is already here, I don't write it again here. So the ones that I'm interested in will be X1 and X3, the non-descendants. Okay, and this is the general rule. So just by looking at the graph, I can make the conclusion. The conditional independencies in this form, they are known as local independencies of the graph because they are conditioned only on xi's parents, okay, that are local to xi. So now let's formalize stuff. First, we define the so-called local Markov independence. Given a graph G, the set of local independencies denoted by IL, L stands for local, of G, I the independencies, and the G for the graph, these will be in this form. Xi being independent of its non-descendants given the parents. Now note that this only depends on the graph. I'm not talking about probabilities here yet. Just if I give you a graph, you can write down these conditional independencies for every of the nodes. Okay? And then I define a map, independence map, or the I-map. G is an I-map for P if the local independencies defined by G are a subset of the independencies of the distribution P. Okay? Now, so G being an I-map for P means that P satisfies the local independencies of G. Okay? So again, the graph G, like here, this graph is imposing some local independencies, this and this. By the way, if I check it for X1 and X3, we will see more examples shortly. Then you can see that X1 condition on its parent is independent of its non-descendants. Well, the non-descendants then will be empty because these are all the remaining ones are its descendants. And X3 also, all the remaining ones are its descendants. So these two will not give me any additional conditional independence. So this graph is imposing two the conditional independencies, and we say that it is an I-map for some distribution P if P satisfies both of them. So this is just another definition. Now here's the key theorem. If we have a graph G, and it's directed acyclic, of course, and P be a joint distribution, then we say that P factorizes according to G if and only if G is an I-map for P. Okay, so here's the thing that we were looking for, we no longer need to do all those original chain rule based factorizations. We can easily just check if a factorization is given. I can just write down the graph. I can check the conditional independencies, the local conditional independencies, and then if P satisfies them, I'm done. I can say that yes, P can be factorized in this way. Okay, and let's see it in practice. Consider the joint distribution P over x1 to x4. Okay, remember the table, so you can imagine that I have a table of a data set P, and then you can use some tests that we will later see in the next chapters to find which variable is independent of the other variable. So here it's saying that x4 is independent of x1 and x2, condition on x3. Now, and its derivatives, its derivations. What do I mean by that? Well, okay, just a recall here. First of all, x4 being independent of x2 and x1, condition on x3, is indeed the same as this when I put them together. So don't get confused. This means that x2, the intersection of x2 and x1. Okay, so I mean the two of them together. Now you may say, is it any different from putting them separately? Well, yes. Of course, if you have this one, like x4 being independent of the two of them, again with parentheses, this will conclude, you can conclude from here that x4 is independent of x2 given x3, and x4 is independent of x1 given x3. So this will be concluded. And by the way, I'm putting x3 in gray to say that it can be conditioned or it cannot be conditioned, it doesn't matter. So you can also talk about like x4 being independent of x1, x2 without the condition. Still, this holds. But then the opposite does not hold. If you have x4 is independent of x2 and x4 is independent of x1, doesn't necessarily hold that x4 is independent of both of them together. Okay? Now, two other minor points. The conditioned part, which is x3 here, can appear on the left as well. So if I have this independence, then I can just write down x3 here as well. Just use the definition of conditional probability and you'll see that it has no effect. Of course, if I know x3, then I will, putting it here, x4 will still be independent of x3, doesn't matter. And the opposite, of course, does not hold as well. Now, another little trick sometimes which can be useful is that the independent term can be conditioned on as well. So here x4 is independent of x2. You can also put it on the right side. Again, you can use the definitions to see that this doesn't matter, doesn't change anything. Okay, good. Now, of course, also the opposite does not hold. So we only have this, but then all of these can be concluded, and you can work out other possibilities perhaps. So it wouldn't make sense to just write down this as the condition at the set of conditional independencies, because all the other ones in the previous slide also hold, but they are kind of trivial, so I don't want to just write all of them down here. In the summary, we will write in the summary table that graph that we work on. I will put them all down. But here, I'll simply write down and its derivations, anything that can be derived from this. Okay? So imagine IP is this. Now, you are asked, does this probability distribution satisfy this factorization? So what I will do, one way was that chain rule based. No, I want to use the graphical visualization. I construct the corresponding Bayesian network structure, x1, x2, x3, x4, and then x2's parents is x1, x3's parents are x2 and x1, x4 is only x3, and then I will write down its local independencies. Now, for x4, given its parent, I know that it will be independent of its non-descendants, so here it's only x1 and x2. Good, so I will write down this. What about x3? Well, x3's parents are x1 and x2, and the remaining is its descendant, so it doesn't give me anything. And the same with x2 and x1. So the only one is this. Okay, now here I don't need to write down and its derivations because we just defined it here very formally. Only these we consider as the local independencies. Okay, just to make things easier. Now, you can see that ILG, the local independencies, are a subset of IP. Well, in this case, this term appears exactly here, okay? And therefore, G is an I-map for P, so P here factorizes accordingly, according to this one here, okay? Now, two exercises prove that P factorizes according to G, not from the theorem, of course. And the other one is that prove that if a joint distribution factorizes according to the above graph G, it satisfies ILG. Okay? It's good for practicing the algebraic derivations that we just went through. Okay, another example. Consider the same P, with the same conditional independence. Does P satisfy the following factorization? This one is a little bit different. If you draw the graph, you will see that, well, in this case, it's exactly the chain rule, okay? So it will be a completely connected graph. And if you write down the local independencies, it will be empty, because for every variable, if you condition it on the parent or the parents, then the remaining ones will be the descendants. So there's nothing to be independent from. And of course, in this case, ILG is a subset of IP. Still, it is an I-map for P, so P does satisfy the above factorization. Another example, the same P, but this time the factorization is different, and if you draw the graph, you will see that it's quite sparse compared to the previous one. X1 is there, X2 is there. For X3, the only parent is X1. For X4, the only parent is X3. Now, what are the local independencies? Well, for X1, we can see that it doesn't have any parents, and all the other ones will be its descendants, so nothing for that. But for X2, condition on its parent, then both X3 and X4 will be non-descendants, so I should put them here. And X3 condition on its parent, which is X1, it will become independent of its non-descendants, X2, and the same for X4. Condition on X3, it will be independent of both X1 and X2. Okay, and you may notice that here X3 condition on X1 being independent of X2 can be concluded from here. You can check the recall again. And this is not a subset of IP. Why? Particularly for this one. Okay, condition on X1. You cannot conclude X1, this one from star here. And you can try to construct a counterexample actually. And the reason is because it's conditioned on X1 only. Okay, whereas this one, all the derivations, so the point is that they're all having this condition on X3 part. Now, what can we conclude? Okay, so P does not satisfy the above factorization because the theorem was an if and only if. And the exercise asks you to construct such a P, a distribution on X1 and X4 so that it satisfies star, but it doesn't satisfy double star. Okay, one last example. Consider again the same distribution with the same set of conditional independencies. What about this factorization? If we draw the graph, we will see this. Okay, X2 condition on X1 as before. X3 this time is condition on X1 and X2, and X4 is condition on X3 and X2. What are the local independencies? Well, X1 and X2 don't give us anything. For X3 also, X1 and X2 are the parents, X4 is the descendant. For X4, however, we will see that X3 and X2 are the parents, and then it will become independent of X1. So this is the set. Now, is this included here? You can try the tricks in the recall and see that it does actually fit in the derivations, and as an exercise show that G is an I-map for P, and therefore it can factorize accordingly. Now, see it in practice. Welcome to the real world. We have this COVID problem with 12 variables, and imagine you have run some tests and you're given all these conditional independencies: social mask and season mask, sorry, and distancing, social distancing are mutually independent. Allergy, flu are independent of each other and of mask and social distancing, giving season, and so on. If you try to write them down mathematically, you will end up with these ones. And this is just 12 variables. Now imagine you have hundreds or thousands of variables, okay? So what is the question? We have all this, and the question is, can the joint probability distribution be factorized as follows? This. How can you answer this? Well, I can try to draw the Bayesian network structure, right? So D, M, S, they don't have any parents. C is conditioned on M and S. U is conditioned on S only, and so on. And you will end up with this. I just wrote the CPDs layer by layer, and we draw this also in a form that it goes from up to down. Now we can obtain the ILG and see if they all appear in the previous slide. Okay, like here. And good luck with that. Okay, so I will do part of it for you. So look, ILG, if you want to obtain it, you need to go from node to node. Okay, for season, for example, here, all the black ones here are the descendants. So, and it doesn't have any parent, so it will become independent of all these blue ones. M, D, C, you can see, B, V. Okay, and it doesn't have any parent. And you can repeat that for M and S to get all these ones. And then for allergy, I do the second layer for you as well here. Allergy will become condition on its parent season, will become independent of its non-descendants. The descendant is this one, black, so all these ones should appear here. Okay, and you can do the same for flu and COVID, and then as another example, fever in the third layer, you can see that here it is conditioned on U and C, the parents, and the descendant will be drug. So all the other ones, like even this one, which is its sibling, considered the parents, it will become independent of all the other ones, okay, if we just know the parents. And lastly, for drug, here it doesn't have any descendants. The parents, I write them down here, and it will become independent of all the other ones. And we will complete that. So we will get ILG. Are these included in IP? Again, so good luck with that. Some of them are obvious, like here, I guess this one, for example, appears exactly in these ones. You can check them, but not all of them. So you can see, for example, look at S. S has only its condition on M. It is independent of M, D, M and D. It's because of the mutual conditioning independence. But you don't see it being independent anywhere else. Yes, it is conditionally independent. But here it's such a strong claim. Now, don't jump into conclusion that, okay, so no, it doesn't fit. Recall that previous example that I left it as an exercise to show that you can conclude it from the derivations. Similar thing can be shown here. So I leave it as an exercise for you. I will just do one part. So again, some independencies are implicit in IP. For example, for this one, only this was shown. Now remember, we don't, for showing this, it's not sufficient to show that S is independent of M, and S is independent of D, and S is independent of C separately. No, you need to show them together. So what about, for example, I try to do this. So I only have these two in that first slide. Now here I want to add C here. And here's the idea. We know from the first one in the previous slide, we know that S is independent of M and D. Which one I'm referring to? It's the one here. Yeah, I'm referring to number one. S and M are independent, and later I will use number 3, okay? So we have this, and then from 3 we know this one, and now here, from this I can easily conclude that I can omit U, so I will end up with this. And now I can show that SMDC, the joint probability, can be written by the definition of conditional probability as C and S condition on M and D times P of M and D. Now, here I know if it is condition on M and D, S and C can be separated. And now I know S is independent of M and D, so I can just write down P of S, and then this one I can get back to P of C M D. And look what happened. This became decomposed into these two parts. So S is independent of MDC together, and this belongs to IP. Now, if you want to add the other one, B, you should use number 6 where it says B is independent of this, and you can try to use some tricks such as if you have C here, you can add it here. If you have M and D here, you can add it on the right side, and you can omit some other ones, and so on. I will leave it as an exercise for you. So, to kind of summarize here, see it in practice, the first question is the above graph an I-map for P? We showed that, meaning that does it factorize accordingly? We showed the answer is yes. Well, partly it is for you to complete the proof. Is it the only I-map for P? Meaning that, is this the only corresponding Bayesian network or the only way to factorize this graph? And the answer is no. One obvious solution is the completely connected acyclic graph. We saw that for the 4-node case, it gives ILG equal to empty set. It doesn't impose any conditional independence. And this is, of course, always a subset of any IG. Okay, so if I just add all the links here, that will be 1. But then is that the only one? First of all, try to prove this in the general case, not just for 4 nodes, for an arbitrary number of nodes. And then I left it as another exercise by trying to delete or add some other links. Can you construct another DAG that is an I-map for P? Okay, yeah. So, summary. Recall the big picture. What was the goal? The goal was to find from data here the correct factorization to reduce the number of parameters. And we saw that, well, you can do it in many, many ways to factorize this. And each of them, we draw the corresponding Bayesian nets. For IP, we assume that we did some tests on this. It's not necessarily true here, it's just an example. But we assume that we have tested and we know that C condition on D, condition on M is independent of D, and M is independent of D as well, condition on C. D is independent of M and C, and of course its derivations means that D is also independent of M and D is independent of C. So we assume that we have the full number of conditional independences here. And then the question was, how from here I can know which one I should use? Now, the idea is to see which one is an I-map, right? So for each of these Bayesian nets, I will write down the corresponding set of local independencies. So for example, for the first one, I know that D is independent of both C and M. Here, I know that M condition on its parent C is independent of D, and I know for C that it is independent of D. Okay, now I will do that for all of them, and then I will check which ones are included here, and the ones that are, then that is our solution. Okay, so for example here, this one, these all are included here, you can check, and the same here, and the same here. So all of these are an I-map, and all of these are a valid solution. There can be several, as you can see, which one we should choose. To see the answer, you can watch the next video. Thanks for your attention.